Hi, let's talk about designing a file hosting service like Dropbox or Google Drive. A cloud file storage service have become really popular nowadays because users want the ease to access the same file from anywhere via any device. So even if they have multiple devices and they want to use the same file or access the same file, then Dropbox and Google Drive comes really handy. Also, in the IT world, Dropbox and Google Drive design discussions are really popular. So let's discuss about the system design or the high level design of Dropbox. Now, whenever we talk about high level design, we need to consider some factors such as availability, reliability and durability and scalability. Because Dropbox is used by millions of users. So it is really important that we properly scale the system. The system should be highly available and reliable and durable. Let's start with the basics first. So, for what purpose do we use Dropbox for? What is the basic purpose of using Dropbox? The basic use is the file and folder. Basically, what we do is we upload a file and we download a file. So that is the basic feature that Dropbox should support. Now, can we use multiple clients? So as we discussed earlier, that a user can have a desktop, a laptop, a tablet or a mobile, and he should be able to access the same file. So the file should be synced. The file should be synced across all its devices. The file is again the most important thing here. So what are the information we need to take care about a file so that we design a proper system? So the first important factor is the file size, because file size will decide how much time it will take to upload a file or download a file, or how much network bandwidth it is going to use. The location. So we need to take care about where are we going to store the file internally. So the location of the file is also important. The next important thing is the versioning, because a same file can be updated and re-uploaded again, or it can be edited online as well. So we need to take care about keeping all the versions of the file. Now that we know the file is the most important component of a design system, let's take an example. Let's say we have a file and we have our server. So when we upload a file, if the file size is 10 KB, it is really easy and fast to upload. But what if it is not 10 KB? What if we are uploading 20 MB file? So it might take some time. But let's say we upload a 20 MB file at once. Now users come and update the same file. So updated file, again we are going to upload the 20 MB file. Even if user has updated a single word or has done minimal changes, we are re-uploading a 20 MB file. If user again comes and again update a slight detail, then we will again upload a 20 MB file. So if we are updating a 20 MB file multiple times, it is a waste of our bandwidth and our storage. It will also give us the latency issues. So what is the better approach to solve this? Now, let's say you have the same file of 16 MB. What if you divide this file into multiple smaller files, and we can call it chunks. So if we divide a single file into multiple chunks, let's say 4 chunks, then each chunk will become 4 MB. So now when we want to upload this file to a server, it will be easier to upload the individual chunks. We can also use multi-threading to upload these individual chunks. But how they are actually useful is, in case you update the file and you update only one of the chunk of the file, let's say chunk 2. Now instead of uploading the 16 MB file altogether, you can only upload one chunk which is of 4 MB. And tomorrow if you again update the same file and you update a different chunk, let's say chunk 4, then again you will only be updating 4 MB. So this way you will benefit by using less memory and using less bandwidth. Our next thing is the metadata. Now that we have discussed that we can break a file into multiple chunks, we need to take care about the metadata information we need to keep in our system. Because based on that metadata information, we will be able to divide and again reconstruct the file using chunks. So in metadata, we can keep the file information, we can keep the versions of the file, we can keep the chunk information, we can keep the chunk order because to reconstruct the file, we need to know in what order chunks are broken into. We can also store the chunk version link because a single chunk can belong to multiple versions or single versions. So we need to know which chunk belongs to which version of the file. At the end, we can also store the hash value. So the hash value can be the hash of a chunk so that we do not upload the same chunk again and again. If it is already uploaded, we do not need to upload it again. This way we again save our storage. So this is the basic metadata information we will have to store if we are going to divide the file into multiple chunks, and we will store the information about versioning of the file. The next thing is the storage. Since we have the file and the metadata, where we can store it. So the file and chunks, we can directly store it on any cloud storage. And the metadata we can store in our database. Now it's better to segregate these two because metadata will have the information required to reconstruct a file, and the file can then directly be downloaded from the cloud storage based on the information present in metadata. Now, the next thing we need to worry about is the synchronization. So, our service should support automatic synchronization between devices. That is, after updating a file on one device, it should get synchronized on all the devices. Because if user updates a version of the file in one device and he still gets the old file from other device, then he might face issues. So, to understand this better, let's assume you have multiple clients, client 1, client 2, and client 3. So, you have a synchronization service. Now, if client 1 updates something in the synchronization service, then synchronization service should also update that information in client 2 and client 3. So, that is also our basic requirement. Now, another thing is the database where we are going to store our metadata information. So database in general are of two different types. One is a relational database and another is a NoSQL database. Now, there are property associated with each kind of database. Since relational database supports ACID properties, but scaling is difficult, the horizontal scaling, and performance with scaling may suffer because if you use multiple shards, then joining them back and keeping schema information and then reverting back the information may be difficult. But NoSQL database does not support ACID properties out of the box. You can implement ACID properties via code, but scaling is very easy. You can horizontally scale the NoSQL database because it is schema-less and the performance is better. So now that we have discussed the basic use case about Dropbox, about the basic use of file, how we can easily upload a file, and the different kind of databases and synchronization topic, so let's design it. Let's design it step by step. Now the first thing we can design is the client side. So client side, when we have a file, we need to make sure that we have all the information related to a file. So we can keep a client. Now in the client, we can keep a chunker, a indexer, a watcher, and an internal DB. What all are these four components? So let's discuss one by one. The first thing is watcher. Now the use of the watcher is it will watch the file. Basically, if user is performing any action on the file, it will take note of that action and it will inform the indexer that something has changed or user has performed any action on that file. It will also monitor the changes other clients published via synchronization service. Now the next is chunker. So chunker is basically responsible for breaking the file into multiple chunks. And similarly, chunker is also responsible for merging the file back from chunks at the time of downloading. The another important feature of chunk is to compute hashes of the chunk to make sure we do not upload duplicate chunks. The next is indexer. So as we discussed that indexer will receive the information from the watcher. Now indexer need to update the internal database with that information. Indexer also need to update the sync service about the new changes and update the metadata database with the information it has received. The fourth component, internal DB, can be acting as a local database. It will store all the information about file and their location, about their version, their chunks, the chunks orders, and their hashes. So basically, it will have the metadata information internally present as a local copy. Now let's talk about the design of the synchronization and concurrency. So one solution is a monitoring service to check changes continuously and upload file. So it can continuously poll if any changes has happened and it will upload the file. But the issue with this solution is basically since we are going to continuously check that something has changed, we might face into concurrency issues. It will require more bandwidth, that will require more storage, and it will uh, produce latency issues as well. So a better solution to this is to use messaging queues. Now in queue we can keep two different type of queues. One is the request queue and another is the response queue. So the task of the request queue will be to update the metadata database with the information it has received. And the task of the response queue would be to send back the response to other clients so that they can update themselves. So if one client has updated something, it will send the request to the request queue. Request queue will send it to the synchronization service, and synchronization service will send it back to response queue so that response queues can send it back to other clients. Now let's look at it via an example. So the design could be something like this. We have multiple clients, we have a sync service and a database. So sync service will update the database. Also we can have queues. So the first is a request queue. So if any of the client update anything, they can send the request to request queue. Now we can also have response queues. So we can have multiple response queues. Now if request queue gets something, then it will update the synchronization service. And synchronization service will again respond back and it will use the response queues to send the new changes to our clients. So this way, all the clients will always be updated with the new changes. Now let's look at the integrated design. So when we say integrated design, it means let's integrate all the components which we have discussed till now. It is not a full design because Dropbox as a whole is a very big use case and it has a lot more components than just uploading and downloading the file. Hence, it is just an integrated design of our client design, our synchronization design, and our database. So what we have designed here is that we will have our file and the client will have watcher, internal DB, chunker, and indexer to monitor it. The indexer will send the data to the queues and the queues will use the sync service to update the database and to send the response back to the other clients. Now, in our database, we will store metadata. All of our actual file will be stored in the cloud. So the important point here is the database. Since we have discussed that we have mostly two kind of databases. One is a SQL database which is of schema and another is a NoSQL database. Here we need to scale the database for sure because Dropbox is a very big use case and it has millions of users and each file can have different versions and each user can have n number of files. So the database needs to store all that information about millions of users and tomorrow a lot more. So our database need to scale for sure. But we need a database which also supports ACID properties because our use case requires a synchronization and concurrency. If we are getting multiple requests, we need to make sure we are following ACID properties and we are moving from one consistent state to another consistent state so that any of the user on any of the device does not find a corrupt copy or a old copy. Hence, using NoSQL is also very difficult unless we implement ACID properties on our own at the code level. What Dropbox has done is they have still used MySQL and they have scaled it horizontally using the sharding mechanism. But what they have done is to handle the use cases of scaling, such as keeping the schema information or the other drawbacks of using RDBMS in a horizontally scaled system, they have implemented a wrapper on top of it. So they have implemented a edge wrapper, and the purpose of this edge wrapper is to do all the computation which DB is supposed to do, and internally it will just make a call to the database. They also have a caching layer to check if any data is already present in cache or to keep the hot data in cache so that we do not make a lot more database calls because caching calls are comparatively cheaper and database costs are comparatively higher. So this is how we can look at the integrated design of Dropbox. Now, there are some important considerations while we design a system like Dropbox. First thing is, what if the client is offline or disconnected in between? So that is the primary reason we are not using REST APIs here. Because if you make a API call and the client is offline, the call might fail. Hence, we use queues. So what happens is, even if the client is offline, queue will store that data in the incoming queue. Now, whenever the client comes online, the client will consume the data from the queue. So that way we never lose any update. The second question could be how to maintain the consistency. Because let's say you are updating a file and a file you might update multiple chunks. So when another client is receiving updates, it might receive chunk by chunk. So is it a good way? Is it a good way for a user to see file getting updated in a parts? Because each chunk is a part. So for client, the whole file is one. But if he sees that only the part of files are getting updated slowly, might not give a correct view for the client. So what instead we can do is we can create a temporary file and we can apply all the changes to the temporary file first, and once the temporary file receives all the changes, we can then replace the actual file with that temporary file. The next consideration could be how to reduce duplication. So this we have already discussed that if we already have a same chunk, then we should not upload it again. Let's say user already made similar changes in the past and he is making the same changes now again. And if the values are exactly the same, then if we upload the same chunk again, it's more like creating a duplicate copies. So how do we reduce it? That is why at the time of discussing metadata, we discussed that we should also create hash of the chunks so that we compare the hash and see if such hash is already present. If it is, then we do not upload the chunk, we only keep the reference of it and we remove the current chunk. So this is it, and there are some other consideration or the last minute thoughts we can think of. Basically, whenever we design Dropbox, we also need to take care about security, about the permissions, a read write, about user account if it is free or if it is premium, about the limit of the memory the user is using if he is free, about load balancing if we are putting some load balancer in front of some servers, about caching strategies, about the hashing strategy used while putting the data into database. So there can be a lot more that we can discuss in this approach because Dropbox as a whole is a very big use case. So it depends on what the topics comes up in the discussion, but we have tried to cover at least the basic stuff that Dropbox design should cover for. Thank you.